Assalamualaikum. My name is Muhammad Aiman bin Alas. I am from Group 3, Section 3, and this is my group members. For introduction, metal casting techniques like polymer processing include a variety of options. Although there are numerous variants between the various casting methods, there are also similarities. In all casting operations, for example a metal alloy, is melt and then poured or pressed into a mold, where it adopts the shape of the mold and solidifies. The casting is removed from the mold once it has set. Within castings, there are two forms of solidification. First, directional solidification and then progressive solidification. For directional solidification, it happens when solidification begins at the far end of the casting and progresses towards the sprue. For the progressive solidification, that also known as parallel solidification, is the process of solidification that begins at the casting walls and advances perpendicularly from the surface. Next is the Cherepov's rule. Cherepov's rule is an applied physics that links the solidification time of a basic casting to its volume and surface area. Under otherwise equal condition, the casting with a big surface area and a small volume will cool faster than a casting with small surface area and a high volume. The connection may be expressed as follows: T is equal to B over A to the power of n, and the ratio of the casting volume to its surface area in the modulus M is equal to V over A. The mole constant of Cherepov's rule can be calculated using the following formula. When Tm is equal to melting or freezing temperature of the liquids in kelvins, T0 is equal to initial temperature of the mole in kelvins, delta Ts is equal to T4 minus Tm is equal to superheat in kelvins, L is equal to latent heat of fusion, K is equal to thermal conductivity of the mole, Rho is equal to density of the mole, C is equal to specific heat of the mole, Rho m is equal to density of the metal, Cm is equal to specific heat of the metal.
Hello, I am Shad. I will explain about the literature review I have conduct for the method of the directional solidification process with metal shell mold. So the method is shown to figure out after the pouring, the same mold is progressively submitted by controlling the exit of the cooling water. So the multi-shell structure may strengthen the thermal insulation effect of the mold. So delay the cooling of the top of the casing to provide a bigger temperature, differentially near the solidification interface along the height direction of the casting. So eventually it is flexible to construct the solidification with the fan of solidification being pushed by the increase the water level. So the next is the Corvinus rule. So you can see the equation which state the total storage time. Ts may be the compound. So V is the value of the casting, A is the surface area, and B is the amount of the constant which depend on the characteristic of the metal being cast. So depend on the density, heat capacity, or heat diffusion. So the equation is M constant B is dependent of the initial temperature, density, thermal conductivity, heat capacity, and watt thickness of ball of the metal and mole. So there's a unit the mole of constant B are second per meter square. So that's all for me.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Khairul and I will talk about the methodology of directional solidification. Okay, first, the flows, microstructure, and casting performance are all determined by the solidification of liquid metal during the casting process, which is primarily influenced by the cooling of the casting mold, contrasted with experimental observation to show their efficiency and accuracy. As a result, one of the secrets to raising casting quality is managing the cooling of casting. Traditional modes for sand casting are dense, making it challenging to provide cooling control. By using powerful bottom cooling, the directional solidification method creates a considerable temperature gradient between the solidified metal and the molten metal in a specific direction, causing the molten metal to grow in the opposite direction of the heat flow. Okay, so next is process that involved in directional solidification. Mostly the process involved in directional solidification is uh, HRS, which is height rate solidification, GCC, gas cooling casting, LMC, which is liquid metal cooling, FBQ, fluidized Z bed quenching, and lastly is ZMLC, which is zone melting with water metal cooling, which is the most frequently used for directional solidification. Okay, next, this is the figure that shows uh, the whole uh, process involved in directional solidification, with where they start with superalloy melt and ending with the withdrawal direction. Okay, next is the important characteristic in directional solidification. Okay, first is the design geometry of the furnace interior, the grain selector, the thickness of the ceramic mold walls, and the positioning, shape, and thickness of the feeder system. Okay, next is the location and orientation of the blades in the furnace cluster and the installation of certain areas of the ceramic mold come next. Okay, and lastly is the superheat of the alloy, preheating time of the ceramic mold withdrawal rate, as well as the conduction and radiation properties of the alloy, ceramic baffle, and the furnace wall material, which generally changes during the process. Water flow rate through chilling chamber walls and chill plate in the furnace cold zone, as well as time dependent heat input the furnace to hot, which is power to heating coils. Okay, lastly, the most method that used in directional solidification method is basic wall method. Okay, the basic wall method is the relative upward movement of the furnace is modeled as a time dependent boundary condition, and the cluster of blade is kept constant to approximate the withdrawal process mathematically. Okay, to do this method, the furnace wall is divided into numerous small surfaces, and each surface is given a unique temperature history based on the moment at which it is crosses the baffle and transition from operating as a component of the hot zone into a part of the cold zone. So this is the figure that shows the how the basic wall method it started, which is they start for the stimulate furnace interior with a straight line, and then it assign thermal histories to each furnace wall node, and lastly is through the cooling chamber. Okay, that's all from me. Thank you.
Okay, my name is Mama Aiman. I will continue about mode verification. Model predictions employing both techniques has been checked against analytical solution, contrasted with experimental observation to show their efficiency and accuracy. For analytical solutions, the primary goal of U factor and radiation calculation is to produce the relatively accurate heat flow to each ceramic mold surface during the course of the withdrawal process. For every mold, wafer, and furnace wall surface involved, standard temperature were assumed. To know more about the standard temperature and the furnace wall surface that involve Q can refer the next slide. Okay, from the figure, make it possible to calculate the view factor precisely while simulating the furnace interior roughly. The radiation exchange inside this enclosure with was computed. And from the table, furnace component assume the in furnace component assume the solution to set a presensitive temperature for the remaining component in the furnace. From the figure, comparison between finite element prediction and analytical heat flood calculation. Then the first figure shows the sharp transition in heat flood achieved on passing beneath the wafer for the furnace geometry and with a perfect wafer. Then the second figure shows that the heat flood curve is much more gradual with the imperfect wafer. The view factor exchange method was able to adjust the reasonably approximate the new heat flood curve. And for experiment measurement, from the table, to further test the accuracy of the model temperature prediction, a cluster of cylinder blade was instrumented with thermocouples and cast into single crystal in a directional solidification furnace at PCC Airport. Model calculation will perform from the experimental geometry and casting condition and plotting cyclic symmetry to model only the single blade in the cluster. And lastly is compare with thermocouple measurement recorded at the center of the tab of the blade. Reasonable agreement is seen. Again, last from me is mode application. The model must be beyond calculating temperatures to predicting the final microstructure and the likelihood of defects. The work has been initiated by developing criteria that relate the likelihood of each defect to parameters derived from the model calculated temperatures. Then from the figure shows the schematically how various files produced in test casting are found. The clause as a function of the models calculated G and R. Okay, G and R can refer from the figure. To connect metric like this, we found the microstructural data criteria are now being created.
Now we are going to experimental setup or component setup. My name is Muhammad Shafiq bin Saleh, CD1900031. So a multi-shell mold structure and water immersion cooling method is presented for directional solidification of a casting. The mold was cooled in a water tank after pouring with the water level gradually rising. Water flow into the shell, spacing and encircle the innermost shell, providing good cooling and propelling the solidification from upward. Meanwhile, the multi-shell acts as an insulator for the casting upper portion. So, the next is a bar with a diameter. We are used a bar with a diameter of 40 mm and head of 150 mm was chosen. A riser of 50 mm was added. The air gaps function as insulation layer for the multi-layer shell sand mold heat dissipation throughout the casting process, reducing heat transmission from casting to mold and from mold to the environment. The insulating effect gradually improved as the number of shell increased to a specific amount. A 4-layer shell mold design was used. There were 4 layers of shell, each 5 mm thick and 3 level of voids, each 10 mm wide. The body cover the multi-shell mold. Next, with the cover removed, the multi-shell mold could be poured into the mold from the top, and the cover could be replaced once the pouring was complete. This multi-shell sand mold were created utilizing a binder jetting 3D printing with a 1.8% addition of furan resin binder, quartz sands, and particle diameter range of 75 to 150 m was employed. A A356 aluminum alloy was melted and maintained at 720 degrees Celsius. From the top, the melt was poured into two identical multi-shell molds, which were then coated with the multi-shell insulating cover. After pouring, one mold was transferred into a water tank and the other was chilled by the natural cooling. Now, as you can see, the table beside in the slide is for composition A356 aluminum alloy. The diagram for A is thermocouple, B is 3D printed sand mold and thermocouple. Next, as you can see at the image, A is pour multi-shell sand mold cooled in water tank. For B, the chart is for water level history for multi-shell mold structure and water immersion cooling method in the water. So the result is, as you can see at 4A, is the cooling curve. The natural cooling requires 27.5 minutes to cool the casting to 400 degrees Celsius, where by using water just use 4.75 minutes. Cooling efficiency was enhanced by 5.8 times. The temperature gradient fluctuation of the two castings in the head direction is shown in figure 4b. That's all from me, thank you.
Finally, for the conclusion, the casting using the MSMWI direct process, the highest temperature gradient, which play a key role in the growth of the casting. MSMWI significantly increase and reduce the of the thereby improving the mechanical property casting. The directional solidification process of the bar casting was realized by gradually immersing the poured multi-shell sand mold into a water tank. Compared to cooling, it greatly improved cooling efficiency by 5.8 and temperature gradient 70 times. The SDAS of alpha grains and the eutectic silicon phase was significantly refined and the mechanical properties were greatly improved, especially elongation by 185%. The proposed MSMWI method is helpful for the directional solidification of alloy.